Good morning, students, and welcome to this morning's class. Today, we want to continue our discussion on time series models. And particularly this morning, we'll be looking at moving average models. So, the question for discussion in this morning's class is what is moving average model? And what do we do in moving average model? It will be clearly spelled out this way. In moving average model, the current value of a variable or series, the current value of a variable or series at time t written as y of t is regressed on its residuals or error terms at the previous time t minus 1, t minus 2, t minus 3 down the line. And the residual at t minus 1 will be written in this class as a of t minus 1. It will equally be written here as a of t minus 2, here a of t minus 3, down the line. That is what we do in moving average model, where the current value of a variable or a series at time t, written as y of t, is regressed against its own residuals at time t minus 1, t minus 2, t minus what, 3, down the line. Which of course can be written as a of t minus 1, a of t minus 2, a of t minus 3. That's what we do in moving average model. Therefore, moving average model can be stated as that the current value of a variable or a series given as y of t is linearly dependent on the previous error terms a of t minus 1, a of t minus 2, a of t minus 3 down the line. That is, of course, what moving average model is talking about. And of course, the moving average of order q, which of course is abbreviated as MA of order q, is written as y of t is equals. We have what? Mu plus theta 1 a of t minus 1 plus theta 2 a of t minus 2 plus theta what? Q a of t minus what? Q plus a of t. Or it can be written as y of t equals, without this mu, you have theta 1 a of t minus 1 plus theta what? 2 a of t minus 2 plus theta what? Q a of t minus q plus a of what? Of t. This is the way to write a moving average model of order q. In the first model, we have the mean constant mu here. But in the second what model, it has been assumed that this mu is 0, and adding it to the what to the model doesn't have effect on the model, and therefore it was skipped. That is what we call moving average model of order Q. It means that there are different kinds of moving average models depending on the value of this Q. When this 2 becomes what? 1, we have moving average model of order 1. When it becomes what? 2, we have moving average model of order 2 down the line. And today we want to look into details moving average model of order 1. So permit me to clean this. I will talk about the moving average model of order 1. Permit me to clean this. In the moving average model of order 1, of course, which is abbreviated as MA of order 1, we are going to look at MA of order 1 by first of all looking at the model. We equally look at what we call the mean. We equally look at what we call the variance. We equally look at what we call the autocovariance. We look at the autocorrelation. And then we look at what we call invertibility condition. Invertibility condition. So let us start by looking at how do we write moving average model of order 1. How do we write each model? Each model can be written in any of these two forms. It can be written as y of t is given as mu plus theta 1 a of t minus 1 plus what? A of t. Let me call this model 1. In the model 2 is where this mean constant has been assumed to be 0. And as such, the model is written as y of t equals theta 1 a of t minus 1 plus a of t. Call this model what? 2. So writing your MA of order 1 in any of these two equations, of course, is okay, as long as you be able to tell us what this mu stands for, the mean constant, which of course in the second model it has been assumed to be 0. So the next thing becomes, how do we get the mean of the moving average model of order 1? To get the mean, what we do is this. You permit me to clean here. We are going to use the first model when we want to talk about the mean of the model. We use the first model. And of course, I have here to be mean. We want to discuss the mean. And we are using that y of t is equals mu plus theta 1 a of t minus 1 plus a of t. To obtain the mean of any model or equation, we take expected value of both sides of the equation. So what I have here becomes that e of y of t is given as e of what? Mu plus theta 1 a of t minus 1 plus what? A of what? T, close the bracket. Okay? Now, to open this bracket, what we have becomes that e of mu plus we have E of theta 1 A of t minus 1 plus we have E of A of what? Of t. And of course, the expected value of a constant is a constant. So here becomes what? Mu plus. I have theta 1, which is a constant. It can be factored outside the word, the expectation sign. And I have theta 1 E of A of t minus 1, close the bracket, plus what? E of what? A of t. And we are going to note something about this A of what? Of t. That this A of t, which we have here, A of t here, this A of t follows normal distribution with mean 0 and constant variance sigma squared of what? Of A. It should be noted that whenever a stationary time series model is written, the error term in that model follows a normal distribution with mean 0 and constant variance sigma squared of what? Of A. So in that case now, the expected value, which is the mean of the error term, is 0 and its variance is what? Sigma squared of what? Of A. With that, we come down to this our proof. And of course, we are dealing with a stationary model. And in a stationary model, we have an assumption that the mean, the variance, and the autocovariance of the model, of course, are constant over time. By implication, the mean of the error term at t minus 1 is the same thing as the mean of the error term at time t minus 2 or t minus 1 down the line. So when we come here, it becomes that this thing becomes what? Mu plus. Here is theta 1, I have theta 1 multiplied by. Here is expected value of an error term at t minus 1, which of course is 0 here. So here becomes 0 plus. Here is expected value of an error term at time t, which of course is 0. Here becomes what? 0. Reason being that the mean of the error term at every point in time is what? Is 0, as long as we are discussing stationary model. So here becomes 0 to this is 0 plus 0 is 0. So what is left becomes what? Mu. So when you use the first model, you arrive at the fact that the mean is what? Is mu. So what becomes the value of our mean when we use the second model? Of course, we already had hinted that using the second model, we are assuming that the mean is 0. But let us of course show it here on the board. The second model says that y of t is given as theta 1 a of what? T minus 1 plus what? A of what? T. That's what the second model says. Where of course we know that a of what? Of t follows what? Normal with mean 0 and constant variance sigma squared of what? Of a. So taking expectation of both sides of the equation as usual, we have that E of what? Y of t is given as E of what? Theta 1 A of t minus 1 plus what? A of what? T. So in that case, opening this bracket, we'll be able to have that E of theta 1 A of t minus 1 plus E of A of what? Of t. Factoring this theta outside, we have that this is theta 1 E of A of t minus 1 plus what? E of A of what? Of t. And remembering what we said earlier, that the expected value of the error term at any point in time is what? Is 0, because the condition is given here. This quantity becomes 0, this quantity becomes 0. And we have theta 1 multiplied by 0 plus 0, and everything boils down to 0. By implication, the mean from the first model is mu, and the mean from the second model is what is 0. By implication, when we are given something like this, y of what of t is given as 1.5 plus. We have 0.2 a of t minus 1 plus what a of what of t. Where we are given information that a of what t follows what normal with mean 0 and variance sigma squared of what of a. And we are told to find the mean of this model. Remembering our proof earlier, we arrived at the fact using the first model that our y of t, expected value of y of t, which is the mean, is given as what? As mu. So what is left for us is to compare this model with the model we know, which is the model for moving average model of order 1. And we are able now to compare the terms. Here is a term with a of t. Look at a of t here. Here is a term with a of t minus 1. Here is a term a of t minus 1. By implication, theta 1 here is 0.2. Here is our mu, and this 1.5 is the only constant here. So our mean of the model here is what? 1.5. However, when we are given something like y of t is equals 0.2 a of t minus 1 plus what? A of t. And we are equally told that a of t follows what? Normal with mean 0 and constant variance sigma squared of what? Of a. And we are told to find the mean of this model. The mean of this model becomes what? 0. Because there is no constant term here, which we call the mean constant. So that is how to go about obtaining the what? The mean. So we quickly go over and look at what we call the what? The variance of a moving average model of order 1. So you permit me to clean here while we go over to the variance. When we want to prove the variance, of course, we are going to make use of what? Of the second equation, or equation 2. Reason being that the variance of a constant here is 0. So including this constant mean, mu, doesn't change anything there. So we are going to make use of the second equation that says that y of t is given as theta 1 a of t minus 1 plus what? A of t. On the condition that a of t follows normal distribution with mean 0 and constant variance sigma squared of what? Of a. And of course, to get the variance of any equation or model in mathematics and statistics, we take the variance of what? Of both sides of the equation. So in that case, what I have here becomes that v, that is var of y of what? Of t, on your permission to write v as variance in order to manage the size of this board. So is equals var of what? Theta 1 a of t minus 1 plus what? A of what? Of t. And we are going to recall for ourselves an existing rule when we are taking variance of two random variables. If you are taking the variance of two random variables, x and y, given as var of what? Of x plus what? Y, where it is known that these x and y are not independent, instead they are dependent, we express this quantity as v of what? Of x plus v of what? Of y plus 2 covariance of what? X comma y. So that is what I'm going to apply here. So I'm going to apply here, I will now say therefore that this my v of y of t is given as, coming to this one alone, I'm going to say v of theta 1 a of t minus 1 plus v of what? Of a of what? Of t plus, I have 2 covariance. Because I have theta 1 here, I can say 2 theta 1 covariance of a of t minus 1, comma a of what of t, close the bracket. This expression is based on this rule. So we move ahead. Do remember that each time you want to factor out a constant from variance sign, you square the constant. So what I'm going to have here becomes theta 1 squared v of what? A of t minus 1 plus. We have v of a of what? Of t plus. It is important that we know that the other terms at different points in time are independent of their own. So there is no correlation between the error term at t minus 1 and the error term at what? At t. Therefore, this covariance here becomes 0. And if this covariance becomes 0 here, when 0 multiplies this 2 theta 1, everything boils down to 0. So what I have here becomes what? 0. And on that note, we return back here. For stationarity of time series model, we are assuming that the mean, the variance, and then the autocovariance at different points in time are constant. By implication, in a moving average model of order 1, the variance of the error term at t minus 1 is the same thing as the variance of the model at time t. Therefore, we have been given a condition here that this error term a of t follows normal with mean 0 and constant variance sigma squared of what? Of a. By implication, here we have sigma squared of a and here we have sigma squared of a. So in that case, I have theta 1 all squared sigma squared of what? Of a plus here becomes what? Sigma squared of what? Of a. There is something common in the terms that I have here. I have sigma squared of a here, I have sigma squared of a here. So I can factor one out. And factoring one out, what I'm going to have becomes that this is theta sigma squared of a, open a bracket. What will be left here becomes what? Theta 1 all squared plus. What will be left here is what? Is 1, close the brackets. So this thing becomes what we call the variance of a moving average model of order 1, where it is known that this moving average model of order 1 is a stationary moving average model to allow the condition that this error term follows normal with mean 0 and constant variance sigma squared of what? Of a. However, in some pages of textbook, somebody might see where they write the variance of a moving average model of order 1, where this 1 comes first. Of course, there is no difference between 1 coming first here and theta coming first here. Because this answer can be written this way comfortably, that we have sigma squared of what? Of a, open a bracket, here is 1 plus what? Theta 1 all squared. The coefficients of the terms here involved are retained here. 1 here is positive, 1 here is positive, theta 1 squared here is positive, theta 1 squared here is positive. So this thing becomes the variance of a moving average model of order 1. Therefore, if somebody gives us something like what I had written earlier, y of t is given as 0.2, we have a of t minus 1 plus a of t. On the condition that a of t follows normal with mean 0 and variance 1.1, for instance. And then the question says, obtain the variance of the model using this model and this information of error term. We quickly come here and look at this. Here we have theta 1. And of course, we are now going to compare this equation given to us with the usual equation of the moving average model of order 1. Here is, of course, the model for moving average model of order 1. We begin to compare this moving average model with the model that is given to us term by term. Here is a of t, here is a of t. So this one is gone. Here is a term with a of t minus 1. Let us come here. Here is a term with a of t minus 1. What is the coefficient of this term with a of t minus 1? The coefficient is theta 1. So by implication, this theta 1 is the same thing as 0.2. So by that, I have known what theta 1 is. And coming to the formula of variance, look at my theta 1 here. So you just need to put 0.2 here and square it. What is now left for you is, how do we get sigma squared of what of A? That sigma squared of A, you have an additional information in the question that sigma squared of A is 1.1. So what you're going to have here is 1.1 into 1 plus 0.2 all squared. And whatever thing that comes out here becomes what we call the variance of the moving average model of order 1. So I want to believe that we didn't have challenge or challenges as we are going about the proof for the variance of the moving average model of order 1. We are quickly going to go over to what we call the autocovariance of a moving average model of order 1. So you permit me to clean here. Let us go to the autocovariance. Okay, for the autocovariance, of course, we are still going to make use of our second model that says that y of t is given as theta 1 a of t minus 1 plus a of what of t. Given that a of t follows normal distribution with mean 0 and constant variance sigma squared of what of a. For us to get the autocovariance of any model in time series, the rule is to multiply the model at both sides with y of t minus k. That is the rule. Y of t minus k. Once you have multiplied both sides with y of t minus k, you now take the expectation of both sides. And by taking the expectation, what of course you'll be getting is what we call the autocovariance. And for that note, I am going to do this. So it becomes, here becomes what? Y of t for the one I have here, multiplied by y of t minus what? K. That is the value of the series at lag k. So this is equals, I come over here, I have theta 1 a of t minus 1 plus what? A of what of t. Open and close, we multiply it with what? Y of t minus k. So what we are now going to do is, fine, we have known what this thing is, but we recall for ourselves. We now say but. We say but y of t minus k is equals. I am going to write its value mimicking what we had here earlier. When we had y of t here, you come here, it becomes t minus 1. You come here, it becomes t, which is exactly what you have here. So if I want to write this one, I'll come here, it becomes theta 1. I have what? A of t minus k. Be what I have here first, before I say minus 1, which is what I have here. I'll say plus. Coming over here, what I have here is t, what I have here is t. But what I have here is now t minus k, so it becomes what? A of t minus what? K. So if you write y of t this way, it implies that y of t minus k will be written this way. So what I'm going to do is to return back here. Wherever place I see y of t minus k, I will replace with this quantity. And doing so, I have that this thing becomes y of t multiplied by y of t minus k is given as what I have first. Open a bracket, we have theta 1 a of t minus 1 plus. We have a of what? Of t, close it. Open again, put the value of a y of t minus k, which is theta 1 a of what? T minus k minus 1 plus a of t minus what? K. Close the brackets. With this, what we are going to do is to begin to make assumption. Let k be equals to 1, get the value. Let k be equals to 2, get the value. But we are going to start from a scratch when we say let k be 0. So we now say when k is equals to 0, when k is equals to 0, when k is equals to 0, what we are going to have becomes, here, anywhere I see k, I am going to put 0 there. And I have what? Y of t multiplied by y of t minus what? 0 is equals, open a bracket. Here becomes theta 1, a of t minus 1 plus a of what? Of t. Close, open. Come here. This is theta 1. Here becomes what? A of what? T. K has been assumed to be 0. Minus 0 minus 1 plus. K has been assumed to be 0, t minus 0. Close the bracket. So this thing becomes what? Y of t multiplied by y of t. T minus 0 is ordinary t. That's what we have it this way. This equals, open a bracket. What I have here becomes theta 1, a of t minus 1 plus. Here is what? A of what? T. Close the bracket, open again. What you have here becomes what? Theta 1. This is minus 0 minus 1. In mathematics, minus 0 minus 1 is minus 1. So what I have is what? A of t minus 1 plus what? A of what? T. Close the bracket. Then we want to open our bracket by saying, let this come over to this come over to this come over to this, and this goes over to that. And by that, we are going to have theta 1 by theta 1 will give me theta 1 all squared. We have what? A of t minus 1 dot A of t minus 1. Okay? So we now have this thing to be, we have, when this has gone to this will now go over to this. We say plus. This becomes what? Theta 1, A of t minus 1 multiplied by this what? A of what? Of t plus. This will come over to this. We have theta 1, A of t minus 1 multiplied by A of what? Of t plus. This will go over to this, and we have A of t multiplied by A of what? Of t. At this juncture, we are going to take the expectation. And taking the expectation, of course, you are going to have that what? E of y of what? Of t multiplied by y of what? T is given as. While we are taking the expected value, we should be careful. So we have this expected value here. Of course, this is a constant. I can keep it outside, which is theta 1 squared E of A of t minus 1 multiplied by A of t minus 1. Close the bracket plus. When we come over here and we are taking expected value, we remember that the error terms at t minus 1 and at t are uncorrelated. And taking their expected value here now will result to 0. So the whole of this quantity here is going to be 0. So for that reason, we are going to skip this quantity or this term. Coming over here, the same thing is applicable. Error terms at t minus 1 and at t are uncorrelated, and as such, 0. The quantity here is what is gone. Then we come here. So we are going to take expectation of A of t and A of t. So we now have what? E of what? A of t multiplied by what? A of what? Of t. And may I remind us that when k becomes 0, we call it autocovariance at lag 0. And another name of autocovariance at lag 0 is variance. So it is written as gamma 0 is equals. What I have here is what? Theta 1 all squared. Of course, expected value of error terms at t minus 1 and at t minus 1 is what we call the variance of the error term, which is given to us as sigma squared of A. So I have sigma squared of what? Of A plus. Expected value of error term at time t and at time t is equally sigma squared of A because of stationarity condition. So here becomes what? Sigma squared of what? Of A. So this now becomes, factoring like what we did before, we are going to have sigma squared of what? Of A into 1 plus what? Theta 1 all squared. And as you can see, that's the reason why people comfortably say that the autocovariance at lag 0 is the same thing as variance. Because this value is exactly the value we had when we proved our variance. So this is autocovariance at lag 0 when k is equals to 0. We are now going to say when k becomes what? 1, what happens? Let us see what happens when k becomes 1, believing that you did not have a challenge in the one we have here on the board. So you permit me to wipe this one. So before we wipe it now, let us call this thing up on the board for us to be seen. So that our gamma 0 is given as sigma squared of what? Of A into 1 plus what? Theta 1 all squared. That's what we have for remembrance purpose. So we are going to say when k becomes what? 2. When k becomes what? 2. So here I have this. The first one we did was when k is 0. So here is when k is what? Is 1. So when k is 1, you return back here. Anywhere you see k, you are going to put 1 there. So in that case, what you are going to have here becomes what? Y of t multiplied by y of t minus 1, because k has become 1. This is equals to, you open a bracket. This is theta 1, a of t minus 1 plus a of what? T. Close the bracket, open again. Here becomes what? Theta 1. You have now known exactly what we are doing. Here, k has become 1, and here is now minus. So I have minus 1, which is minus 2. So I have what? A of t minus what? 2 plus. Here becomes what? A of t minus 1. This is what we are going to have. So we do what we did before by opening the bracket. This quantity goes to this quantity. This quantity goes to this quantity. This one goes to here, and this one goes to here. So this thing becomes that what we now have becomes this going into this will give us theta 1 all squared, a of t minus 1 multiplied by a of t minus 2. This has gone into this plus. This is now going into this. We have theta 1, a of t minus 1 multiplied by a of t minus 1. This has now gone into this. It becomes this one. So we have plus. When this one goes over to this, we have what? Theta 1, a of t minus what? A of t multiplied by a of t minus what? 2 plus. This will now go into this, which is a of t multiplied by a of t minus 1. So we want to take the expectation now. So taking the expectation, we say therefore that our e of y of t multiplied by y of t minus 1 is now given as. We should also be mindful of the kind of expectation that we take here, bearing in mind that the error terms at different time frames are independent or uncorrelated. So meaning that at time t minus 1 and at time t minus 2, this a of t and a of t are uncorrelated, and taking this expectation reduces the entire of this place to be 0. We come over here. This one we have t minus 1, which of course is going to turn to variance. So we take its expectation. So it becomes what? Theta 1 e of what? Of a of what? T minus 1 multiplied by a of t minus 1. Close it. We come over it. Here error term is at time t minus 2, uncorrelated 0. At time t minus 1, uncorrelated 0. So the only thing we have is left now is this. We now have. And do remember that when you are talking about when k is equals to 1, you are talking about autocovariance at lag 1. Autocovariance at what? At lag 1. Written as gamma 1 is given as. Here becomes theta 1. Of course, the expected value of error term at t minus 1 is the variance, which is sigma squared of what? Of a. So I'll comfortably say, attach here, that our gamma 1 is given as a theta 1, then sigma squared of what? Of a. We have succeeded looking at the autocovariance when k is equals to 0, that gave us this. When k is equals to 1, that gave us this. Let us try and look at when k is equals to what? 2, because there is a statement that says that the moment you exceed the order of the moving average model, the autocovariance reduces to 0 automatically. So let us see whether once we exceed this 1 here now, whether we are going to arrive at what? At 0. So we can categorically say that when the lag is less than the order of what is greater than the order of what of the model, the autocovariance is 0, which will of course imply autocorrelation being 0. So let us clean here. So we are going to say when k is equals to 2. So when k becomes what? 2, what we are going to do, anywhere we see k, we are going to put 2. And here we are going to have that y of t multiplied by y of t minus 1 will be given as bullshit. Here is what? Here is a t, a k, and we are taking k to be what? To be, sorry for that comment. So, and the k, we are taking it to be 2. So here becomes t minus 2 is given as, here is my theta 1, a of t minus 1 plus a of t. Open again. We have theta 1, a of t. Here it is now 2. Minus 2 minus 1 will give me minus 3 plus a of t minus 2. Close the bracket. So when we are opening the bracket, this goes to this. And when this goes to this, what we are going to have becomes theta 1 all squared a of t minus 1, a of t minus what? 3 plus this to this will give us what? Theta 1 a of t minus 1, a of t minus 2 plus this to this will give us what? A of t, and then will give us, when this goes to this, we have what? Theta 1 a of t and a of t minus what? 3 plus this will go to this. We have a of t and a of t minus what? 2. And we should now note that when we want to take expected value, we say therefore a of what? Y of t minus what? 2 is equals. Here the error terms are at time t minus 1, t minus 3. They are uncorrelated. So this quantity becomes 0 when you take the expectation plus. Here it is t minus 1, t minus 2. So this quantity becomes 0 when you take expectation plus 0. Here is t and t minus 3. So it goes down to what? 0 when you take expectation. 0 plus. Here is t and t minus 2, which becomes 0 when you take expectation. This is 0, which is equals. And then, of course, you know that when you talk about the expected value of y of t and y of t minus 2, you are saying that k is equals to 2. And we call it autocovariance at lag 2, written as gamma 2. So, gamma what? 2 is equals to 0. And therefore, we can then say that gamma what? 2 is equals to 0. What can we learn from this? That when, of course, the number of the lag goes beyond the order of the what of the model, the autocovariance becomes what? 0. And using what I have on the board, it implies that when someone gives us that kind of equation I wrote earlier, that y of t, for instance, is equals 0.5 y of t, no, a of t minus 1 plus what? A of t, where our a of t follows a normal distribution with mean 0 and variance 1.3, for instance. And we are required to find the gamma 0 as usual, required to find the gamma 1, of course. Here is our theta 1. Theta 1 here is 0.5. It goes in here. This is sigma squared of A, which is 1.3 in the condition of what? Of A of t. The same thing applies in the variance, what we have explained earlier. 0.5 goes over here, square it, add it to 1. Outside the bracket, it becomes 1.3 because that is the variance of the error term. And these, of course, are the various autocovariance functions of MA of order 1 at different lags. So what we are going to do now is to quickly look at the autocorrelation, which is, of course, an extension of autocovariance. So permit me to clean here. So when we talk about autocorrelation, autocorrelation. So which of course is this one, the autocorrelation. When we talk about autocorrelation is represented with a rho k, where k is the order of the lag. Autocorrelation at lag k. This is given as what? Gamma k all over gamma 0. Where of course our gamma 0 is what we call the variance. So if I want that to go and find the autocorrelation now of the MA of order 1, it is now going to be that my row 1 now here, my row 1 is given as, or let me even start from row 0 and show you something. This is row 0, this is equals to. So row 0 you are saying autocorrelation at lag 0, that time that k is equals to 0. So here is going to be gamma 0 all over gamma 0. And do remember that gamma 0 is in the numerator, gamma 0 is in the denominator. So you can cancel 1 and cancel 1, it becomes 1. And this is the reason why they say that the autocorrelation at lag 0 is always 1. Because you'll be having ratio of variances, which cancels off to give you 1. So we now move to when k becomes 1. So when we now have what? Row 1, it is going to be gamma 1 all over what? Gamma 0 is equals to. Our gamma 1 here is what we have as a theta 1 sigma squared of what? Of A all over. Our gamma 0 is what we have here, which of course is sigma squared of A into 1 plus what? Theta 1 all squared, close the brackets. So here I have sigma squared of A, here sigma squared of A. This and this can be cancelled off, and I have theta 1 all over 1 plus theta 1 all squared. And this thing become the autocorrelation at the lag 1. So at autocorrelation at lag what? 0 now, or at lag what? 2 now, is going to be our gamma 2 all over what? Gamma 0. And our gamma 2, of course, was 0 earlier. So this thing becomes what? 0 all over this variance, which is a sigma squared of A into 1 plus what? Theta 1 all squared. And as long as 0 is the numerator, everything reduces to what? To 0. So which means even the autocovariance, even the autocorrelation, once the lag goes beyond the order of the what of the model, they all become 0. And people say that the autocorrelation function of MA of order 1 cuts off after order 1. That is K when K is greater than or equal to what? 2. But they have a value when k is strictly less than what? 2. That is when k is 0 and when k is what? Is 1. That is how to get the autocorrelation of MA of order 1. When they are asking you a question using that kind of a model, for you to obtain the row 0, which is 1, and for you to obtain row 1, of course, you use this particular quantity. That equation we gave earlier here was 0.5 all over 1 plus 0.5 all squared. We'll be able to give you the autocorrelation. Thank you very much for your audience for today. We have just given attention in detail or totally on moving average model of order 1. In our next class, we might be looking at the moving average model of order 2, paying attention to all these outlines. Same apply to the remaining part of our discussions on autoregressive models, that is AR model. Remember to subscribe to our YouTube channel and keep track of our classes.